Today, I will be presenting on the nature of myoglobin, more specifically, the denaturization of myoglobin. Myoglobin is a globular protein found within the muscles. Myoglobin will store oxygen in the muscles that can be used when muscles are doing work. Myoglobin consists of a single polypeptide chain and a heme ligand. The heme ligand is partially exposed to the surface, with the majority of it buried within the protein. The oxygen will bind to an iron atom located at the center of the heme ligand deep within the protein. Oxygen's nonpolar nature makes it insoluble in the blood, therefore myoglobin is essential for providing oxygen to muscles. In the picture, the red represents the heme ligand, and the blue is the oxygen bound. The pink is the rest of the myoglobin protein. Guanidine hydrochloride is a strong organic base consisting mostly of guanidine ions at physiological pH. It is also a natural product of protein metabolism. Guanidine hydrochloride is a protein denaturant and can inactivate many proteins and enzymes. The goals of this experiment were to determine the equilibrium constant for the denaturization of myoglobin, as well as the Gibbs free energy of unfolding of myoglobin. Recent evidence suggests that the protein misfolding and aggregation may play a role in the development of diseases such as Alzheimer's, cystic fibrosis, and cataracts. This experiment will provide integral insight into the protein unfolding that can be expanded upon in future studies. Two hypotheses were used for this experiment. One was as the concentration of guanidine hydrochloride increases, the absorbance of the sample will decrease. This is because guanidine hydrochloride as a denaturant will cause myoglobin to unfold. The unfolded conformation of myoglobin will absorb less light than its folded conformation. Another hypothesis was the Gibbs free energy of unfolding will decrease as more guanidine hydrochloride is added. As more denaturant is added, the unfolding of myoglobin will be more favorable, and the Gibbs free energy will decrease and eventually become negative. In order to investigate protein unfolding of myoglobin, various concentrations of guanidine hydrochloride were added to phosphate buffer and myoglobin. Fisher brand Elite micropipettes were used to transfer stock solution to disposable centillion vials to make 19 sample solutions. This can be seen in the picture shown. An absorbance spectra of each sample was then taken using Werner UV-Vis Spectrometer Plus in conjunction with LagerPro. This spectrometer utilizes an LED and tungsten bulb to transmit light through a diffraction grating. The diffracted light is sorted and collected by the linear CCD array detector. UV-Vis spectroscopy has a quick response time, high sensitivity, and relatively low cost, making it a good choice for this experiment. The maximum absorbance in the Soret band for samples was used to determine the equilibrium constant for each sample. A Soret band, also known as a Soret peak, is an intense peak in the blue region of the visible spectrum. The Soret band mainly arises from pi to pi star transitions. The equilibrium constants were then used to determine the free energy of unfolding. The various concentrations of guanidine hydrochloride used can be seen in the table on the slide. 1 milliliter of myoglobin solution was used for each sample, and each sample had a total of 5 milliliters. To avoid clutter, only 5 of the 19 runs are shown in the spectrum. The table provides the full scope of the data. The runs are numbered with increasing concentration. Both the spectra and the table show the decreasing absorbance as the concentration of denaturant increased. The likelihood of myoglobin denaturing without the presence of a denaturant is low, and it can be concluded that the more denatured the myoglobin is, the less light it will absorb. These results agree with the first hypothesis. The Soret band also changed with the concentration of denaturant. In general, the wavelength of maximum absorbance decreased with the increase of guanidine hydrochloride concentration. This wavelength shift is known as blue shifting. This figure shows the absorbance versus the concentration of guanidine hydrochloride. Here we see a backwards S-shaped curve in the graph. AN is the point where there is a complete absence of denaturant, and AU is the point where there is an extreme excess of denaturant. And their absorbances are labeled on the graph. The box portion of the graph is from 0.9 to 1.2 molar guanidine hydrochloride. When the concentration of guanidine hydrochloride is at 0.9, the denaturation process becomes significant, as we can see the absorbance starts to drop dramatically with the increase of denaturant. The most rapid change in conformation of myoglobin is seen within the box. Within this section, the protein is in the process of unfolding, and we see a more linear relationship between the concentration of denaturant and the absorbance. These values will be used to calculate the equilibrium constant for the denaturization of myoglobin and the Gibbs free energy of unfolding. At concentrations below 0.9, the myoglobin is mostly in its folded form. By 1.8 molar of guanidine hydrochloride, most of the myoglobin is in its unfolded conformation. The equilibrium constant was calculated using the equation shown, where KQ is the equilibrium constant, AN is the absorbance with no added denaturant, and AU is the absorbance of excess denaturant as shown in the previous figure. A will be the absorbance at the given point. In the table, we can see the equilibrium constant will increase with increasing denaturant concentration. Essentially, this tells us that increasing denaturant concentration will increase the rate of unfolding. At zero concentration of guanidine hydrochloride, the equilibrium constant is zero, meaning that the unfolding of myoglobin will not take place. The Gibbs free energy of unfolding was found using the equilibrium constant and the equation shown. Delta G is the free energy, R is the gas constant, 8.3145 joule per mole Kelvin, and T is the temperature, which was a standard 298 Kelvin. Between 1 and 1.05 molar of guanidine hydrochloride, the free energy becomes negative, meaning it is more energetically favorable to fold the myoglobin and will be a spontaneous process. This data supports the second hypothesis. At higher concentrations of denaturant, the unfolding of myoglobin is more energetically favorable. As the 1 molar of denaturant, products will be favored in equilibrium, and more myoglobin will be in its unfolded conformation than its folded conformation. The concentration from 0.9 to 1.2 molar were plotted against the free energy. Their linear relationship best represents the actual process of unfolding. The slope and intercept of the trend line were found using LINEST and Excel. The free energy of unfolding can be related to Gibbs free energy of water through the equation shown. The free energy of this process in the absence of denaturant occurs in pure water and is represented by delta G H2O. The slope is the rate of change of the free energy of denaturization with respect to the concentration of denaturant. This value was very large at 25,498.4 joules per mole. This large value indicates denaturization is a rapid process with the addition of denaturant. The large positive value of free energy in water was 26,926.78. This large value indicates that the unfolding of myoglobin is unfavorable in the absence of denaturant. Myoglobin is primarily in its folded form. Value Cm represents the concentration of denaturant when the amount of unfolded myoglobin is equal to the amount of folded myoglobin. This will make the KEQ equal to 1 and the Gibbs free energy 0. The Cm concentration could then be solved for by setting 0, and Cm was found to be 1.056 molar with a standard deviation of 0.1306. The experimental fraction of unfolding was found with the equilibrium constant using the equation shown. The theoretical fraction of unfolding was found using the solver function in Excel. The initial values used were the experimental values for slope and Cm. The error was minimized using chi-squared. The figure shown shows the fraction of unfolded protein, both theoretically and experimentally, versus the concentration of guanidine hydrochloride. The table shows the slope and Cm values used for the experimental and theoretical calculations. The shape of the theoretical fraction of unfolding is an S-curve. Around the concentration 0.9 molar, the fraction of unfolded protein drastically increases. Then around 1.4 molar, most of the protein is in its unfolded form. From this experiment, data supporting both hypotheses was found. As the denaturant increased, the equilibrium constant and in turn reaction rate increased. Additionally, the increasing denaturant concentration resulted in decreasing free energy of unfolding, meaning the unfolding of myoglobin becomes more favorable with the increase of denaturant. Enthalpy is responsible for keeping the native protein folded. The unfolded protein will have more possible conformation, which would increase the entropy. Therefore, entropy would favor the unfolded form of myoglobin. Myoglobin will remain in its folded form in the absence of denaturant because it is enthalpically favorable. During the denaturation process, bonds must be broken within the protein. The breaking of these bonds will increase the enthalpy, making it unfavorable for the protein to be in its unfolded form. A future study could be performed by measuring the rate of denaturization versus the change in temperature to test this hypothesis. A high temperature would allow the bonds to break more easily and should increase the rate of denaturization. With that, I would like to acknowledge the University of Pittsburgh Department of Chemistry, Dr. Wagner, my lab instructor, Sydney Giles, and Tyler Perrick as my graduate TAs, and my partner, Madeline Cherry. Thank you all for your time.